Welcome back to Calculus 1. This is part 2 of our lecture introducing the product and quotient rules. Make sure you are comfortable with all the examples within part 1, as well as the basic statements of the product and quotient rules. Just as a quick test, see if you can write down the product and quotient rules correctly before continuing within this part. We're going to jump in this part into several more complicated examples. When you're ready, let's get to example 3. All right, so at this point in a face-to-face course, in my face-to-face Calculus 1 course, we would have gone through several simple examples. Those were in part 1. And then now for example 3 here, now that you have a sense for how product and quotient rules are working, I would typically turn this over to students to make an attempt at. So pause the video, give yourself an attempt at these. This is going to rely on several ideas we pointed out in part 1. Something about different ways to rewrite, the idea of divide and conquer, identify what your numerator and denominator f and g of x are, maybe identify f and g of x as the factors if you're applying the product rule. See what you can do with these 2 parts. We'll check in several minutes. All right, now when you're ready, let's go through part A. This one is a straightforward application of the quotient rule. There's really no other ways to rewrite this function. So we just will approach it as a quotient. F of x, the numerator, will be square root of x. And then g of x, the denominator, will be x plus 1. All right, notice f of x as square root of x. We can easily differentiate that if we rewrite it, which is one of our kind of central problem-solving techniques we've mentioned so far. So to calculate the derivative of square root of x, rewrite it as x to the 1/2 power, and then it's really easy to differentiate using the power rule. Okay, so that is pretty much most of the work calculating those individual derivatives. This would be the dividing portion of what I called divide and conquer. So we have all the pieces we need, the 2 functions, f and g, and their derivatives. Now we just combine them back together using the quotient rule, since we're identifying our function y here as a quotient. All right, now when we go to plug this in, the answer for the derivative actually simplifies considerably. Now there's nothing wrong with leaving f prime written as 1/2 times x to the negative 1/2. I prefer just to see some algebraic equivalent versions, just to make some of the steps in simplifying a little easier. So let's rewrite f prime as a fraction 1 divided by 2 times square root of x. So you might recall negative powers go as factors into the denominator, and then a 1/2 power is equivalent to a square root. All right, so let's use that version for f prime. We'll just combine all the pieces together with the quotient rule. All right, and what we get here, which is very common at this point in calculus and beyond, if you're continuing through the calculus sequence, we get what is technically called a complex fraction. We have a fraction where the numerator itself contains a fraction. So we have an expression here that contains fractions within fractions. All right, now there's several ways you could simplify this. What I like to advocate is a very quick way to eliminate the fractions within fractions. Notice in the numerator from f prime, we have 2 square root of x within that kind of a fractions denominator within the numerator. All the other terms, which are not fractions, have denominators of 1. So we can use the LCD, which would be 2 square root of x. And what I'm going to do is multiply the numerator and denominator by that. Notice something over itself is 1, which we're algebraically allowed to multiply by. And the reason for doing this is if I now distribute that 2 square root of x to everything in the numerator, we'll end up having that denominator within the numerator cancel out, getting rid of the fractions within fractions. Okay, so we're just going to distribute 2 square root of x to each term in the numerator. Hopefully the arrows indicate what we're distributing to. And when we distribute to the first term, the 2 square root of x factors cancel out. And then notice when we distribute to the second term, just square root of x, a square root times itself cancels out. So with that little tip there of eliminating the fractions within fractions using the LCD, the least common denominator, we very quickly simplify our answer for the derivative, which is going to be helpful later on and with the ideas we get through later in the course. Now just to notice the 2 square root of x that was in the denominator in red there, that also had distributed to the denominator. So we have, for our denominator of y prime, 2 square root of x times x plus 1 squared. The benefit of going through this is we no longer have fractions within the numerator. We just have a single big fraction rather than a fraction where the numerator contains fractions. Okay, and that's really the key to simplifying our answer for the derivative here. You can just combine the like terms in the numerator, and we can express our derivative, the numerator, as negative x plus 1, and then the denominator 2 square root of x times x plus 1 squared. All right, when you're ready, we'll take a look at part B. And this one, I think as it's written, I'm tempting you to apply the quotient rule, which you can do. But what I'd like you to do is try this, ignore the directions or the hint there, maybe try this without the quotient rule. I'd like you to try this, reattempt this, try rewriting the function first. I'll give you several minutes for that, then we'll check in. There is a way to do this problem without the quotient rule, which I want you to see with this example. So pause, rewrite the example, and try to apply the product rule. We'll check in maybe 2 minutes. All right, now what's the key here to being able to avoid using the quotient rule? We're going to rewrite before we even differentiate. And that, again, is a really important problem-solving technique at this point in Calculus 1. Because notice here, if we rewrite the square root of x in the denominator as x to the 1/2 power, a power in the denominator we can rewrite as a negative power. So we can rewrite this whole function, the original quotient, without fractions. We can rewrite it as x to the negative 1/2 times e to the x. And since we've rewritten this as a product, we can now apply the product rule. Myself and a lot of students find the product rule easier to apply than the quotient rule. So from here, let's use the rewritten version, and then we'll differentiate that version. So the idea is we rewrite before differentiating here. All right, and it actually becomes a straightforward application of the product rule, just maybe seems more complicated since we have fractions within the exponents, but the power rule still applies to differentiating x raised to the negative 1/2 power. All right, so identify your pieces. And the calculation, really the most difficult part is just being comfortable with f of x as x to the negative 1/2, applying the power rule to that. We bring the exponent down. That's where the negative 1/2 factor comes from. But then we subtract 1 from the exponent. So negative 1/2 minus 1 is negative 3/2 if we use a common denominator, which we always will. Okay, that's all the work. This is, again, the dividing part. And now we can just assemble the pieces, conquering the problem. So we combine everything back together using the product rule, not the quotient rule. we're solving this in an alternate way by rewriting first and then applying the product rule. So we combine the pieces here using the product rule. And that's basically it. Now, what we mentioned earlier in part one, this was example one, we're going to see exponential functions a lot. They're very important to calculus since e to the x is its own derivative. Very common for us to take this end result for y prime and simplify it. Notice each term has an e to the x in it, so we can factor that out. And that's going to be something standard that we'll do through examples. We're going to look at a follow-up to example 1a. We're going to have that as a follow-up to example 4 that we'll be getting to momentarily. Okay, so that's pretty much it for example 3. Again, make sure you're comfortable with the ideas here. What we'll be looking at in example 4 is calculating a second order derivative. And we'll kind of see here the idea of we might want to simplify our derivative, but we might not want to simplify it too much. We're going to explore that in example 4 when you're ready. All right, let's move on to example 4. And this one is going to be multi-purpose. So example 4 here seems different. It's basically giving us the position of a function at time t. So there's an object moving along a straight line, a coordinate axis, and its position is changing with respect to time. So we're going to call the position function s of t instead of f of x. All right, so the position of the object, s of t here, equals t squared times e to the t. All right, and what we're going to ask is have you find the object's velocity and acceleration. Okay, now we briefly talked about this earlier, and we haven't talked about it since we really didn't have any of the differentiation rules available at the time. Well, now since we're getting through product and quotient rules, now is a good time to revisit those ideas. With position, the velocity is the first derivative of position, so we can say the velocity is s prime, and then the acceleration, which is the rate of change of velocity, and velocity is itself a rate of change of position. That gives us the idea here that the acceleration is the second derivative of position. Okay, and that probably makes this question more complicated since it's layering kind of some physics concepts into our calculus course, but the two were developed side by side and they complement each other, so I'll make sure to throw those in right now. Okay, now all this, basically just to summarize it, we're given the position, s of t. We just have to calculate the first derivative, s prime, and then differentiate that again to get the second derivative, s double prime. That would give us the velocity and acceleration. Now, this is also going to be a follow-up to example 1a. If that example is not familiar, go back, rewatch the lecture just so it's clear why we're giving a follow-up now. We mentioned something in example 1a about simplifying, but not simplifying too much. And that's rather subjective. We're going to see that come back here. So I'd like you to make an attempt at this. So we're just changing the variable from x to t. We still differentiate using the power rule. And the derivative of e to the t is still e to the t. We're just using a different independent variable, t, instead of x. Okay, so pause, give yourself an attempt at this, and you'll likely encounter some of the difficulties that I anticipate when you're trying to calculate the second derivative to get the acceleration. So we'll check in several minutes, pause, make an attempt at this. I actually hope that you get stuck. That's going to indicate you have something to learn, and then we'll give a follow-up on that, which I think will be a good opportunity to learn a lot of aspects of calculus. So we'll check in several minutes. All right, when you're ready, let's go through first finding S prime, the first derivative of position, which is velocity. That was exactly what we did in example 1a. We have just changed our variable from, at the time it was x in example 1a, but now it's t. Okay, so S of t here is t squared times e to the t. Since we're multiplying, we differentiate using the product rule still. All right, so we differentiate kind of term by term. The derivative of t squared would be 2t. We then multiply that by the second function, e to the t. And then we take the first function, t squared, and then multiply that by the derivative of e to the t, which is itself. All right, so that should be straightforward, I hope. Since each term after applying the product rule contains an exponential function as a factor, we can factor out e to the t here. All right, now this is where we're going to pause to see, depending on how we express the derivative, s prime, the velocity, that could greatly influence the work needed to differentiate that again, getting the second derivative, s double prime, which physically represents the acceleration. All right, so here we have both versions for the velocity, s prime, that we just calculated. The first version written there is not the fully factored or fully simplified version. We only have the exponential factor factored out, e to the t. And it's that first version there with only the exponential factor pulled out that I'm going to advocate is better for calculating a second order derivative. Now, it is mathematically correct. You can see within the parentheses, you can still factor out an additional factor of t, which is the fully simplified version there, t times t plus 2 times e to the t. That second version I'm going to claim is not efficient for calculating a second order derivative here. The reason for that, take a look at the two versions. The product rule, as we've been using it, applies when you have one function times another, which that first version, t squared plus 2t times e to the t, has. You have a function of t times another function of t. The middle version there, that first simplified version for v of t, only requires the product rule once. The problem with the fully simplified version, where we factored out t, is that now has three factors, and the product rule, as we have been using it, only applies when you have two factors or two functions. Now you can iterate, apply the product rule several times to that fully simplified, fully factored version, but the middle version there only requires the product rule once, which is why I advocate that version, only factoring out the exponential function as the kind of preferred version to calculate higher order derivatives. Okay, now as a follow-up to example 4, we'll use this example to explore a new, more general version of the product rule, but that'll be its own follow-up after this. So if you got stuck, maybe follow my recommendation, use v of t as t squared plus 2t times e to the t, that's the version in the middle there, and apply the product rule once to that. That seems very straightforward, I hope. That would give you the second derivative for position, which physically represents acceleration. So try that. We'll check in about a minute. Okay, I hope this is straightforward. Again, it's straightforward if you use this partially simplified version with only the exponential function factored out. It's a lot more complicated to use the fully simplified version, t times t plus 2 times e to the t. All right, there's the work for divide and conquer. F of t is t squared plus 2t. G of t is e to the t. And the derivatives are pretty straightforward there. All right, we just recombine our pieces together for the acceleration, applying the product rule yet again here, and we get our formula here from the basic product rule, f prime times g plus f times g prime. All right, the rest of here to complete it, notice again, each term has an exponential function, so we can factor that out and then combine some like terms to get a nice looking simplified version for the second derivative, the acceleration as t squared plus 4t. 4t is coming from 2t plus 2t, and then plus 2. All that is multiplied by e to the t. So the two answers here would be the velocity function there, which we found by differentiating s of t once, and then the acceleration where we differentiated a second time to get the acceleration as a second derivative. All right, so again, make sure you kind of understand what I was advocating. Don't necessarily simplify all the way. It could actually make it harder for calculating higher order derivatives like a second order derivative here. When you're ready, when you completely understand this example, we'll give a follow-up to example 4, which explores a more general version for the product rule with 3 functions. But that's when you're ready. All right, so let's advance. Example 4 is completed. The follow-up that I want to look at is, again, going to get you towards how mathematics works. Nobody makes things up in mathematics. It's all built off of a rigorous foundation. And we'll kind of show you how that works here. I realize some of you might not care about that. Some of you do, however. Either way, you'll get a nice alternate version that would allow you to re-answer example 4. We're going to explore here how you use the product rule when there are 3 functions or factors being multiplied, f times g times h. All right, so first off, what we have on the screen here is just our basic version for the product rule as we've been using it. All right, what we're going to do is kind of extend our function here to be not just f of x times g of x, 2 functions or factors, but we're going to multiply by a third function, h of x. So we're going to ask if we have a function y equals f of x times g of x times h of x, where f, g, and h themselves are all functions, how do we differentiate this? Now, you can iterate the product rule, but I'd like you to pause and make an attempt to see if you can generalize the 2-factor version there to what you might expect for the 3-factor version. And this is kind of how higher level mathematics and research in mathematics proceeds. We take in a result and then maybe try to make it more general. I'll give you just a few seconds to see if you can write down a proposed formula here. All right, now I'll give you a hint. The way the product rule works, take a look at the second version there, is we differentiate only 1 factor at a time. So the version with 2 factors, first we differentiate the first factor, f, keep the second factor the same, and then we add to that the first factor times the derivative of the second factor. All right, we'll give you a hint here. We can generalize that here to say, well, let's differentiate the first factor, f, but then keep the second and third factors the same, times g times h. See if you can now generalize that with this hint. All right, well, the product rule above has us differentiate the second factor. So we might expect a term like this, f times now the derivative of the second function or factor, g prime, but we keep the third factor or function h the same. Now you're probably starting to see the pattern. Can you write down the final third term? I'll do a long dramatic pause. I feel confident that some of you can. All right, and if you had it as f times g times h prime, that is correct. And that's how we generalize make sure you see the kind of the similarity to above, the two-factor version. This is the correct version for the product rule when there's three functions or factors involved. We're not going to encounter that in many places in Calculus 1, or beyond for that matter, but it's still useful. We can actually apply this new formula to example 4. All right, so I'd like you, if you're aiming to do extremely well in the course, which you all are, retry example 4, finding the acceleration using the fully simplified version, which we did not advocate earlier going through example 4, since we didn't yet have this 3-function or factor version for the product rule. Apply that here. We're going to use v of t as t times t plus 2 times e to the t. We now have 3 factors, f, g, and h. And you should be able to get the same answer for the acceleration a of t. So give that a try. That's a great thing to follow up with me or your professor on, just to make sure you can apply this, which is a bit of a higher level concept, but if you feel comfortable with this, you'll be in good shape for the course. All right, so that concludes what I wanted to address from example 4 and its follow-up. What I want to take a look at is one last final example that is getting a little bit on the more abstract side for examples. It's going to be a little more conceptually challenging, not at all computationally challenging like some of the past few examples within this part of the lecture. So when you're ready, let's move on to the last example, example 5. All right, and here it is. This problem looks short. It's very short to state. It starts off, we have a function, capital F of x, and we could name this whatever, so the names don't matter for functions. But the function, capital F of x, is defined as x cubed times some unknown function, g of x. What we are told in the problem is not an explicit formula for g of x, but rather we're given information for the values of g and its derivative at x equals 2. So we're told g of 2, the y value is 1, and then g prime of 2, the derivative, slope of a tangent line at 2 equals -1. All right, the question wants you to then find capital F prime of 2. Now, this is a little challenging for most students. It's not the computations, but it's kind of conceptually challenging. How do we apply the product rule if I don't know what the formula is for g of x? Well, that's what makes this a little abstract. It is a straightforward application of the product rule. Just leave g of x as g of x and express its derivative as g prime of x. That might be a hint to get you started. I assure you the calculations are simple. Give it a try and we'll check in about a minute. All right, when you're ready, let's start by applying the product rule to differentiate capital F of x, since it's defined as x cubed times, that's the product, g of x. All right, I assure you this, in terms of calculations, is simple, but conceptually, I realize it probably is challenging since we don't have a formula for g of x. But if we have that second function as g of x, we just write its derivative as g prime of x. And that's pretty much it. So we have all 4 pieces, but not as explicit formulas for x. That's okay. So with f of x as x cubed, the power rule gives its derivative as 3x squared. And we just combine all the pieces together. So this is the dividing into simpler problems. And now we conquer our problem by combining the pieces with the product rule. Okay, and as long as you're comfortable with that, that's pretty much the difficult part for the question. We just leave g of x and its derivative as g of x and g prime of x. All right, now the question does want us to get capital F prime evaluated at x equals 2. So to finish the problem, we just replace all x's. This goes for inside g and g prime. Those are functions of x. So we have to plug in x to those functions as well. All right, and this is where we use the extra given information in the problem. We're not told a formula for g of x, but we are given its values for the function and derivative at x equals 2. So we just replace g of 2 with 1 and g prime of 2 with -1. And then it's just a matter of simplifying that, which actually for me is the hard part. I screw up with the basic math all the time. Calculus and advanced nonlinear pseudo-differential equations are fine, but the basic math always screws me up. And I'm pretty sure if you multiply that out, you'll get this comes out to 4. So capital F prime of 2 equals 4. All right, and that's basically it for part 2 of this lecture, concluding all parts for introducing the lecture on product and quotient rules. You will see some examples like example 5 scattered in the homework, and they're similar questions using an abstract application of the product rule as we did here, and there's some where you use an abstract application of the quotient rule. All right, what I just want to close is just a brief summary of the ideas that we've found scattered throughout parts 1 and part 2. The lecture in any calculus course where the product and quotient rules are introduced is very important. So hopefully your professor, wherever you would take it, especially with me, since I'm doing that now, would close with just a summary and overview of a lot of the ideas that were introduced. So the first, what we mentioned for a lot of examples, was the problem-solving technique of divide and conquer. So take a complicated problem, split it into several simpler problems, solve those simpler problems, and then reassemble, combine the pieces to solve or conquer the original complicated problem. We'll continue to use that once we introduce the final differentiation rule called the chain rule. All right, a second idea that we used scattered throughout the different examples in parts 1 and part 2 was we might actually have an easier way to solve a problem finding a derivative if we rewrite it first using some algebraic ideas. So we'll again continue to advocate that it might be better to rewrite the function before you do any calculus, before differentiating using the product and or quotient rules. All right, and then a third and final tip, what we saw scattered out through one of the examples already within this lecture. This was one of our first examples. We might have an easy time to calculate the derivative, but it might be a whole other thing to then simplify that, which is what we saw within our first example of this part. So once you calculate your derivative, try to simplify it. That's going to make some of the questions we'll be getting to within a few lectures considerably easier if we have a simplified derivative when we start introducing the concepts of what are called local and absolute maxima and minimum, as well as something called critical points. Okay, so that concludes everything I wanted to go through with you for the product and quotient rules. Go back and review these different parts, all the examples, as you go through the homework questions. I think you'll be quite prepared for everything in the homework now.